Or I can continue.
Now you can continue. Just let me. Okay, I think. Good. Okay.
Thank you very much. I was saying that these are the only assumptions needed for the potential. Simply, the potential is a positive function, non-negative function that is zero vanishes only at 2 points, -1 and +1. And it's very important that the second derivative at the two minimal point, f double prime, is in plus or minus 1 is strictly greater than 0. We will see what happens later in the talk. What happens if this derivative is 0? I mean, in general, f could have other local minima, but the global minima are only -1 and +1. Just for the talk, you can think that f of u is exactly this function and with this formula. Not important. The general assumption. Now, what is a consequence of this form for the reaction or for the potential? That if we look for traveling wave solution for this equation, and a traveling wave solution is a solution of this form. P of x minus Ct, where P is called the wave profile and C is the real number. The real number is the wave velocity. And okay, when we look for traveling wave solution, strictly monotone, and that connects to equilibrium, actually we are interested in the traveling wave connecting the two minimal points, global minimal point, -1 and +1. There is a very easy computation you can do. If you assume that a solution like this exists and you could substitute this answer in the equation, you do some very basic math and you arrive at this relation. At this relation, the velocity c times the integral of p prime squared is exactly equal, if you want, at the integral of the reaction, or the difference between the potential evaluated at +1 and -1. So for the particular form of the potential, since f of +1 is equal to f -1, this means that the velocity is 0. So you don't have, in the case of the Allen-Cahn equation, you don't have traveling wave solution. You have what they are called standing waves. Your wave does not move. It's a stationary solution. You can study the existence of this profile. The question is very easy. And in the particular case, when f is the one I gave you in the first slide, you can explicitly compute the profile, and it's the hyperbolic tangent of x over epsilon. This is the graph. I wanted to tell you something about the standing wave. It's important to notice that the profile goes very rapidly to plus, minus, and -1, exponentially rapid. When epsilon goes to 0, the profile goes to a step function, -1, +1, and there is this transition point that here is 0. And it's very important to notice because the picture maybe can confuse you. This profile P never touches plus or -1. Never. Actually, the derivative P prime is never 0. It's always strictly positive. This remark is important when we study stationary solution in a bounded interval with homogeneous non-boundary condition. This can never, you can never truncate this profile and have a stationary solution for the problem in a bounded interval. Of course, this solution is unique up to translation. Hyperbolic tangent of x minus h over epsilon is always a solution. And you have also the other standing wave, the one connecting -1 to +1, the decreasing one. Simply you can take minus p of x or p of minus x. Is an odd function, so in this case it's the same. Now, what is the consequence of the existence of these standing waves? Or if you want, the non-existence of traveling waves. Let's choose a particular initial datum for the equation. This is an initial datum I choose. And in simply, gluing together traveling waves, standing waves. Okay, as I told you, it's a solution. We can translate the standing waves. We can put the transition in H1 in a generic point. Actually, here there are n transition points. And let's say this is a decreasing standing wave, and then we glue together this with the decreasing standing wave. Here again, the picture is can confuse you because this function is not infinite. Okay, remember what I told you about the derivative. You arrive here, the derivative is strictly positive, and here is strictly negative. If you zoom in the point where you group together, the point where we group together is simply the middle point. So we have something that is continuous. Actually, this is an H1 function, but it's not infinity.
So and is this a weak solution of the problem, or what kind of solution?
This is not a solution.
It's not a solution. You're not gluing things.
Yeah, I'm gluing it. Simply gluing it.
Okay.
And also, it's not a solution for another important fact. The boundary points. Okay. Remember the profile, the derivative of the profile is never zero, so the boundary conditions are not satisfied. So this is a solution. It's a good question from Alberto. Actually, this is not a solution. This is not the solution for these two problems, let's say, how we connect and the boundary condition. So what happens if you consider this as initial datum and you start your equations? No? Now, it is well known, or you can see numerically, let's say, I don't know, that a profile like this persists for a very long time. This is called metastable state. Metastable state for the equation, because for a time of order exponential of c over epsilon, where c is an important constant, but I won't discuss it. The important thing is that c does not depend on epsilon. You will see for a time of this order, exponential of c over epsilon, this profile, this structure. That is unstable because it is well known that for reaction diffusion equation of this kind, the only stable solution are constant and are the minima of the potential. So in this case, the only stable points are -1 and +1. So eventually, you will lose this structure. I will show you a numerical solution in the next slide. But this structure persists for this very long time. This is a very long time when epsilon goes to 0. When epsilon is very small, this is very big. This problem has been studied since the first paper of '89. There are also some unpublished notes before this, but anyway, very long problem. I want to mention only some results because there are a lot of results. And in these first three papers, they study exactly this problem. Let's start with the well-prepared initial data. Some well-prepared initial data. Of course, not this. Let's say a perturbation of this. And they prove that the solution maintains this structure for an exponential long time. So the first three papers are only about the persistence of this structure. And they are different because Carpio and Fuscodel used a different approach with respect to Bronzer-Cahn. I will talk later when I will present our result of the energy approach of Bronzer-Cahn. But just let me tell you some words on the dynamical approach. The dynamical approach is much more difficult. This is a paper of 15 pages, and you can apply this energy approach in many equations. For instance, in the generalized Allen-Cahn and Cahn-Hilliard equation that I will show later. I will show you later. The dynamical approach is very difficult. It's like 55, 60 pages of the paper of Carpio. And actually, it's no problem to apply this dynamical approach to in the case of nonlinear diffusion, let's say. But the paper of Carpio is very interesting because the evolution of this profile depends only on the interaction of the transition points. And they found an ordinary differential equation describing the movement of the points. And with this ordinary differential equation, you describe the evolution of a PDE of the solution of the PDE. But I don't talk about the result of category, simply an open problem. Then there is this paper of Chen in 2004. This is very important because this paper shows that this phenomena, the phenomenon of metastability, is not, it's a general phenomenon for Allen-Cahn equation, meaning that this phenomena, this persistence of a steady structure exists for a general class of initial data, not only if you choose the initial data in this way. And to explain this, I will show you a numerical example, so a numerical solution. This is the equation. I choose epsilon 0.1. Okay. The initial datum here, I don't know if you can see, but it's very important, is this one. Here, the initial datum is only a step function. Okay. It's like very small here, like 0.01, positive. Then jump negative, like minus 0.01. An initial datum like this is sufficient. Why? First, because it's a parabolic equation. So even if the initial datum is not discontinuous, as you turn on the equation, the solution becomes continuous, C infinity. And important thing is that in some region, your solution, your initial datum is strictly positive. In other ones, is strictly negative. This is sufficient because Chen proved that in the first phase, the evolution, the dynamics is very clear. There are different phases. In the first one, it's like you can neglect the diffusion. Epsilon is very small. The initial datum does not depend on epsilon. So the first phase of the dynamics is governed by the ut minus capital F prime of u. So where the initial datum is positive, the solution goes to +1, close to +1. Where is negative, close to -1, without touching +1 and -1. This is important. So in a very small time, relatively small time, t equals 9, you have this structure. The structure I show you in the previous slide.
So here the roots are any points, or they are specifically chosen?
No. That's very important. Arbitrary. Totally arbitrary. You can choose the points like you want. It's very important this because it is well known that the stationary solution for the Allen-Cahn equation in a bounded interval with homogeneous normal boundary condition are constants and periodic. So if you choose the points in a very particular way, periodic, this is a stationary solution. So you can say, okay, it's going to a stationary solution. No, because the points are totally arbitrary. And anyway, it can go to the periodic solution because the periodic solution is unstable. The only stable are -1. After this, after the creation of your metastable state, the solution maintains the structure for a long time. Actually, this is t equals 1000. Here, also it's for real. You cannot, it's not the screen. You cannot see difference. It's like the solution didn't move. Here the same. Here you see it moved because the transition point interacts. This is not a stationary solution, and they attract each other. They attract each other, and this happens. When they are very close, suddenly the transition disappears, collapse. Okay, this is 1230. And here again, it's like the profile doesn't move. At the end, the limit as t goes to +infinity is -1 or +1. In this case, it's -1. This is t equal to 10,000. You lose the transition here. Here, there is still the transition, but it's moving to the boundary. Okay. So, what we are interested now in the talk is to study the persistence. So, only this, if you want, only this line. This is called generation for the metastable state. This is called annihilation. Okay. So a metastable state for a very generical class of initial data, it is sufficient that the initial datum has n zeros. Change is time. No. There are n changes time. If this happens, this is the dynamics. But we are interested only in the persistence. So the goal of this talk, or the first goal of the talk, is to understand what happens in the persistence of the metastable state in the case of the generalized Allen-Cahn equation. Our question was simply, from the mathematical point of view, what does it change if instead of the linear diffusion, we consider the p-Laplace operator in 1D? This is the p-Laplace operator for any p greater than 1. Okay? If p is greater than 2, strictly greater than 2, we have a degenerate equation. Okay? When ux is equal to 0, the diffusion is 0. If p is in between 1 and 2, this is the singular diffusion. No, it's like ux in the denominator. So the question was, what happens if we consider the same problem, homogeneous boundary condition, in a bounded interval with the p-Laplace? And we understood that, very important, the reaction, the competition, the balance, if you want, between the p-Laplacian and the reaction, the potential. So we realized very fast, actually, that it's better to consider a more general potential. Is here, there is a power theta. So it's in the classical case, here you put the power is 2. Here we put a generic power theta greater than 1. So this is called generalized Allen-Cahn equation, because generalize the Allen-Cahn equation for two things, let's say. First, the p-Laplacian, and then the potential is more general. The Allen-Cahn equation is simply this one with p equal theta equal 2. But we consider any generic p and theta greater than 1. And this is the potential. If theta is greater than, this is red, this one, theta equal 2 is the classical potential. If theta is greater than 2, we lose the important assumption f double prime in plus or minus 1 equal to greater than 0. The second derivative here is 0. There is no the picture of theta in between 1 and 2. In theta, in between 1 and 2, you have to be careful because the potential is only C1, it's not C2. Okay, in plus or minus 1. So let's start to study this equation by studying the standing wave. The computation is the same as the Allen-Cahn equation. You can prove that there are no traveling waves. The velocity c is 0. So let's start by studying the standing wave. This is the question for our standing wave, monotone and connecting plus or minus 1. We put p of 0 equal to 0 just to have let's say a unique solution. The solution is unique up to transmission. There is no modulus here because the profile is monotone, and easy computation. You multiply the equation for p prime. This for p prime is times p prime is a derivative. This times p prime is a derivative. So you arrive something, derivative is equal to 0. So we have an energy. We have something that is constant, and this constant is 0. This constant is 0. This is constantly equal to 0 because you compute this when x goes to plus or minus infinity, and you take advantage of the fact that p prime at plus or minus infinity is 0, and f of plus or minus 1 is 0. So you arrive at this particular equation for the profile, and at this Cauchy problem. First order Cauchy problem. This is the equation for the profile. This is the condition only to have a unique solution. Well, separation of variables, very easy. The solution, your profile P, is implicitly defined by this relation. I wanted to write this relation because it's very important. What means? What does it mean? What does this relation mean? It means that if I take, for instance, a real number between 0 and 1, okay, the integral, let's say alpha, the integral between 0 alpha of this thing multiplied by epsilon and this constant is exactly actually the time for the space. Usually, this is the first order differential equation, so I can confuse with time, but this is space. It's the space that you need to arrive from 0 to 1. No? Okay. What happens if I want to connect 0, 1, 0 minus 1? This is completely symmetric, no problem. I have to study this improper integral, 0, 1 of 1 minus f squared theta over t.
So do you have an explicit expression for theta, maybe for some values, for pi, sorry, maybe for some values of theta, or?
Yes.
Okay.
I will show you only one.
Okay.
But probably you can find some more explicit solution. Yes. For theta equal 2 is very easy, and I will show you. But also for, I think, I don't know, 2 theta over p over. I mean, if you fix p, for any p, I don't know. I think it's very easy. But if you think in particular cases, yes. Okay. Anyway, this integral is a improper integral, but is finite if theta is less than p. That's why I said we immediately realized that it's better to change, also to consider a generalized potential. Because if theta is not, I mean, it's very interesting to study for any theta. If theta is less than p, this integral is finite. So this means that there is a finite value of the variable x, such that you touch plus or minus. And you arrive very smooth, actually. You arrive very smooth. It's the same like when you have the ordinary differential equation x prime equal to square root of x. So you have infinitely many solutions. Another important thing is this integral is a number when theta is less than p. The time, the space you need to reach plus 1 is epsilon multiplied. Okay. So it's very small when epsilon is small. It's linear in epsilon. Epsilon times constant. Constant that depends on p and t. Since you reach infinite time or infinite space, the two minima, you have much more solution, much stationary solution, because this profile, the profile that is infinity up to the point, okay, but it's a classical solution that is important. It's a classical solution, so I can find many stationary solutions of my problem. This is the stationary problem. If theta is less than p, I can totally arbitrarily fix a number n, and totally arbitrary. This totally arbitrary is very important. H1, H2, Hn in AB, that are your transition point. And actually, you can do the same as I did in the previous slide with the hyperbolic tangent. You glue together your standing waves. But in this case, it's a stationary solution. And it's a stationary solution because, yes, this is a classical solution. And the position is totally arbitrary because you don't care. Let's say that you put two transition points. I don't know, you can put it very close, it's not the problem. The point is that you can choose epsilon so small such that the transition is very fast. And when you arrive here, you can stay constant, no problem. And then you connect. And this is for totally arbitrary points. Sorry.
So whenever you touch the constant 1 and minus 1,
you can stay constant.
And it's with derivative 0, with minus derivative 0.
Yeah. Probably use some derivative, it's not infinity the connection, but not the first one. Or if you want, it's simply the question. This is for sure satisfied. So this is very important. Totally, the number of the transition, you can put all the transition you want in AB, and the position is totally arbitrary.
And it's always bounded between 1 and minus 1.
Yes.
Never goes down.
No, because it's simply the construction. It's simply by using this. And this is exactly touching -1,1. And this tells you, if you want, this gives you another explanation of the metastable phenomena of the slow motion result in the classical case. But it tells you that there is no need to study metastability when theta is less than t, because you have stationary solution. Actually, more than metastability, you should study stability. A stationary profile like this is that if you take a perturbation of this, okay, when t goes to plus infinity, you lose the structure or not. This is the problem. Metastability will be only a partial result. You could say, okay, I take a perturbation of this, I will keep the profile maintains this structure for an exponential of time. Well, but maybe it maintains this structure for any time because it's a stationary solution. So in the case theta less than t, there is no need to study metastability. And this is an explanation, if you want, only also for the metastability of the classical case. Because it's like if you fix t equal to, okay, so linear diffusion, it's like you can perturb the potential. Let's say a potential theta. For theta equal to, it's not a stationary solution. But for theta less than 2, as soon as theta is less than 2, this is a stationary solution. So the solution u theta, let's say, is stationary for any theta less than 2. But for theta equal to 2, it's not a stationary. It's not a stationary solution. So what happens? I can tell you theta less than t is called subcritical case. The case theta equal to is called critical case. Theta greater than t, supercritical case. When theta is greater than or equal to t, the integral is infinite. You are in the same situation of the classical linear diffusion, let's say, and the classical potential. You never touch plus or minus 1. But there is an important difference between theta equal to t and theta greater than t. When theta is equal to p, actually you can explicitly the solution is always of course, there is only the constant that change. Theta equal to p is 1. So it's hyperbolic tangent. There is a difference in p, but not p is greater than 1, so no problem. So we have an exponential decay of the profile towards the state plus or minus 1. But if theta is greater than t, you don't touch, the profile doesn't touch plus or minus 1, but there is algebraic decay. You go algebraically fast, not exponential, you go slower. And these two facts are important consequence in the slow motion of the solution. Because now we are interested in this study, the slow motion of the solution when theta is greater than or equal to. And I will do that by considering the energy approach of Gonzalez-Hahn, as I told you. Okay, so what is the energy for this kind of equation? Well, in general, for this equation, no matter what is the potential, this is an energy. This is very easy to check if the solution is is sufficiently smooth. You multiply by using the equation, and you arrive at this relation. The variation of the energy is equal to the L2 norm in space and time, or ut. This is very important. This is in general. In our case now, it's important to consider not this energy, but to denormalize the energy, to divide by epsilon. And I will show you the next slide because it's important to divide by epsilon. So our energy, this is our general. This is, if you want, a generalized Ginsburg-Landau function. Okay, when p is equal to, and that is a lovable potential, this is called Ginsburg-Landau function. I know the Allen-Cahn equation is the L2 gradient flow of the Ginsburg-Landau function. In this case, we have a generalized Ginsburg-Landau functional. We divide by epsilon, and we arrive at this relationship. This relation is important because it's the key estimate to prove slow motion. Your velocity, the L2 norm of the solution, now I put epsilon because it's exactly the solution of this equation with, let's say, f with that specific form. The L2 norm of the of ut is simply the energy at time 0 minus the energy at time t. This is the key estimate to prove slow motion, because the goal is I want this to be very small. This difference to be very small. So to be very small for t very large. So if t is very large and this is very small, ut is very small, slow motion. This is roughly speaking. Okay. And in order to have, there is no energy. There is no energy to move, to change the structure of the profile. And this prove that this is very small. This is simply energy at time zero, so assumption on the initial data. What is very important is to have a lower bound on the energy at time t for very long t. And this can be obtained by using a variational result. In this slide, there is no equation, there is no partial differential equation. It's only a result about the energy function. Why we divide by x for this computation? We have a sum here. This is the energy, no? Something to the power p plus something. We use the generalized Young inequality, a to the power p over 3 plus b to the power q over q is greater than or equal to the product. We apply this inequality. Of course, we have to understand what is the q, okay, and we arrive at this. If we assume that u epsilon connect -1 and -1 is monotone and connect -1 and -1, change of variable, here you have constant depending on p, and here there is only something depending on the potential level. We call this constant Cp. Actually, we divide by epsilon so that here we have Cp, a strictly positive real number that does not depend on epsilon. Okay? If I don't divide by epsilon, here there is epsilon Cp. I don't want this. This Cp is very important. When you put p equal to, you always recover the classical result. Anyway, when this number is very important because it's the minimum energy to have a transition between -1 and -1 and +1. Actually, we can prove this result. This result is only true when theta is equal to p. When theta is greater than p, we will have another result. I will show you later. So if the potential, if we choose theta equal to p, and we fix a piecewise constant function, this is a function with n transition, totally arbitrary, in h1, hn, totally arbitrary. If we fix this b, and we fix this real number a, there is no time to discuss a, then we can prove that there exists positive constant such that epsilon 0 c delta, such that if, this is equally important, if u is close, u is here is regular h1. If UH1 is close to V in L1, you can prove that the energy, there are n transitions, so it's greater than or equal to NCP minus an exponentially small remainder. This is for any theta equal to P. This estimate, this is here, the equation plays no role. We are simply talking of the function. This variational result allows us to prove exponential promotion of the solution. Very fast, very fast. Let us assume that the initial datum goes to V, that is fixed. This condition simply fixes the number of the transition and the position. Okay, when at the, let's say at the initial time. Assume that when epsilon, the initial datum depends on x. When epsilon goes to 0, tends to be in L1, and assume that the energy is not so big, is the minimal energy to have a transition plus an exponential small remainder. Well, in the case theta equal to P, it's written here, we have this exponentially slow motion result. We can prove that the solution U epsilon P converts to V in L1 as epsilon goes to 0 for any t exponentially large. Okay, so this is simply telling you the solution maintains the same structure of the initial datum for any t here for any exponential large t, time t. This estimate is true for any t because the energy is increasing, no, along the solution. This result tells you this is also true for any t here. So it's like the solution maintains the same structure of the initial datum. And the proof of this is long. I don't want to give you the details, but it's based on what I told you. The fact that you can estimate the L2 norm of t with the energy. The energy at time 0 satisfies this assumption. At time there exists a time t star. This is the difficult part to prove. That there exists a very large t star epsilon such that the energy at the time is greater than or equal to NCP minus exponentially for the mass. And to prove this, you need the exponential, the variational result. When you substitute these two estimates, you have that the L2 norm of ut is very small. And this is enough to prove exponential promotion. Now, this is simply an example that you can construct a function satisfying your assumption. And the example is simply the one I showed you at the beginning, gluing together the standing waves. This is not the stationary solution. But let's go to the result in the supercritical case when theta is greater than p. When theta is greater than p, you don't have a variational, you don't have a lower bound with an exponential small remainder. Here you have only an algebraic small remainder. And this, the power of your algebraic small remainder is given by a sequence, by this sequence. Okay. Of course, it depends on p and theta. Anyway, you can only, the result is almost the same. You need another assumption here, but this is technical. The point is this: if u is close to v in L1, you have a lower bound, but with an exponential, with an algebraic small remainder. Thanks to this, we can only prove that the solution maintains a stable structure, the same structure of the initial datum, only for an algebraically long time. It's very important what is the power. The power is kappa j, where kj is in this sequence. The previous example, if you construct the standing waves, I mean, if you use the standing waves to construct the profile, that profile satisfies this with simply with 0. It's less than or equal to 1. Okay, you never touch minus 1 and plus 1. So actually here, you can put all the number of the sequence. So what is the behavior of the sequence? Very important. Here, theta greater than p plays the crucial role. Because if theta is greater than p, this alpha here is in between 0, 1. This is an increasing sequence, but the limit is finite. The limit is this number. So this is the, let's say, the biggest power you can put here is theta p over time, theta minus p minus 1. Notice that when theta and p are close, this is for theta greater than p. So when theta, let's say, goes to p plus, this alpha goes to plus infinity. But this is what we expect, because we know that for theta greater than p, this is true for any natural number. Actually, it's true with exponential. Okay, but this is a result for any theta and p, for any theta greater than p, and this is the power. It's a finite power that, for instance, goes to plus infinity when theta goes to p plus. Now, Cahn-Hilliard model. Is it late? Can I talk?
It's okay. You can go on for 10-15 minutes.
Okay, 10 minutes. I want to discuss also the Cahn-Hilliard model. Now it's a third question we consider in this study, in this talk, sorry. Cahn-Hilliard model. This is the generalized Cahn-Hilliard model. This is the question. So what do we have here? First, P of u. This is it is a let's say density dependent mobility. This is called mobility in the Cahn-Hilliard equation. Actually, when the model was proposed, when the Cahn-Hilliard model was proposed, here there was a non-constant mobility depending on it. But then much of the work, the first work went, okay, let us assume that this is constant. And usually in the Cahn-Hilliard model, this is constant. Here is density dependent, but it's very important. It's strictly positive. We can, our results all true for any d strictly positive. Then we have p-Laplacian and our f that is exactly like before. This is a generalization of the Cahn-Hilliard equation. What is the Cahn-Hilliard equation? Is p constant, p equal to, and potential with theta equal to. So we generalize for three reasons: p, and theta. We consider this equation in a boundary interval again with homogeneous normal boundary condition. Now you have to be careful. What is no-flux condition? What are the no-flux conditions in this case? Okay, it's exactly this, and this is very easy to see because solution the first important difference with the Allen-Cahn equation. The solution of the Cahn-Hilliard equation conserve the mass. So if I integrate between a and b ut, I want this to be 0. I integrate here. There is a derivative. So I simply have to compute this and a and b. And these are exactly the boundary condition. So these conditions are relevant from the physical point of view because they ensure that the solution preserves the mass. The integral of AB, an integral between a and b of u doesn't change in time. It's important to write the boundary condition in this way, actually, because when theta is in between 1 and 2, this is not C2. Why? Because if this were C2, the second term is simply f double prime ux. And ux is 0 at the end. So it's like for theta greater than or equal to, you can stop here. Only this x equal to 0. But in general, we have to write in this way because f is not 0. What happens in the case of the Cahn-Hilliard equation? This is the Cahn-Hilliard equation. D equal 1, P equal 2, and f with theta equal to. The dynamics is different from the Allen-Cahn equation. I mean, simply you have the persistence of a steady structure, but there are some differences that I want to point out in these slides. First, for the Cahn-Hilliard equation, there are two things. First, the solution preserves the mass. Second, every constant is a solution. In the Allen-Cahn equation, you have only 3 constant solutions. The 0 of the reaction, if you want the critical point of the potential. Here, two derivatives here, any constant is a solution. So the generation of the steady structure of the metastable state is very different. You can prove that there is an interval that contains 0 where the constant solution are unstable. Okay. And this is called spinodal interval, spinodal region, or if you and this process is called also spinodal decomposition. It's not so easy like the Allen-Cahn equation. In the Allen-Cahn equation, to have a metastable state, you simply need something positive, something negative, and that's it. Here, it's not clear what are the mathematical conditions, let's say, to have something like this. There are some papers, but let's say that the conditions are not so natural. Anyway, if you start with the perturbation of a constant in this spinodal region, you always have something like this, your unsteady structure. Here, the initial datum is a random perturbation around 0. It seems 0, it's not 0, it's not constant, it's a random perturbation. In Marta, you say random perturbation 0, very small, and this happens. Very small. This is t equals 0.2. When you have the transitions, the evolution is 2. Why I put this picture? Because it's very important. In this case, the first point, the first transition to disappear is the last one. But I hope you can see it. There is a big difference with the Allen-Cahn equation. In the Allen-Cahn equation, you simply lose the transition. In the Cahn-Hilliard equation, that cannot happen, simply because there is conservation of mass. If you do this, the mass is left, or it's different. So what happens? That yes, here the point disappears, but this point is moving too. This point goes there, and this is attracted, so lose that. So here you lose mass, and you gain mass here. Another situation now is a generic, another solution with 5 layers. I have 5 transition points. I like this because it's exactly what I show you in the Allen-Cahn case. No? The 2 closest transition points, these are the 2 points that disappear. They disappear, so you lose mass here. How you gain it? Simply because this point move, follow this, and this point follow this. So the mass that you lose here, you get here. And at the end, in a situation when you have 2 layers, they simply move in a rigid way. The two layers move the same towards the same direction and with the same velocity. So they move in a rigid way, and there is no loss of mass. And until you arrive at the boundary, and you arrive something like this with 1 transition. Another important difference with the Allen-Cahn equation is that any profile with 1 transition is stationary and stable. So in the case of the Cahn-Hilliard equation, you have conservation of the mass, and you arrive to a profile with only 1 transition. You cannot arrive to -1 or +1 because, of course, the mass, I mean, not of course, but probably the mass is different. So this is the dynamics of the Cahn-Hilliard equation, the classic case. What happens in the generalized Cahn-Hilliard equation? First, let's study the stationary solution. Simply, ut equals 0, this is equation. This is constant, homogeneous non-boundary condition, and this is 0. There is another derivative here. du doesn't play a role. Doesn't play a role because is all this equal to 0. Okay, and this strictly positive. So is all this equal to 0. All this equal to 0 means that this is constant. Beta. So for any beta in R, this problem, gives you a stationary solution of the Cahn-Hilliard equation. So no way to describe all the stationary solution of the Cahn-Hilliard equation. For any real beta, solve this problem and you have a stationary. Much more complicated. But for instance, if beta is equal to 0, this is exactly the problem we studied before. Stationary solution of the generalized Allen-Cahn equation. So any stationary solution of the generalized Allen-Cahn equation is also a stationary solution of the generalized Cahn-Hilliard equation. In particular, the compactors, that solution I introduced like 20 minutes ago, are solution also for the generalized Cahn-Hilliard equation. So this is simply to tell you there is no way, there is no need to study metastability slow motion when theta is less than.
So for theta less than b, you have this stable solution, but they are stationary solutions. They are stable.
We don't know.
Okay.
We don't know. Actually, for the Allen-Cahn equation, there are some works, and it's not. Let's say that there is. They give the authors give some assumption like that. Yes, it's not a stationary solution. As t goes to ∞, they tend so asymptotically stable. But it's an open problem because it's not easy to understand what perturbation you need. No? You have your stable state. You perturb it in which way? Any perturbation, it's not clear. In the Cahn-Hilliard case, I don't think there are results. Anyway, now we have to study what happens if, I mean, in the case theta greater than, when theta is greater than or equal to p. It's possible to construct maybe for some beta, because I have much more solution. It's possible to construct stationary solution like this for any H1, Hn, for totally arbitrary stationary points and totally, I mean, number. So we have to study this boundary value problem for any beta. Let's study for beta. Okay, let's for any beta. Let's introduce this. This is easy. So your potential here is the reaction, if you want, is f prime minus b. So the potential is f of u minus b. So you have the same problem as before with the non-balanced potential, g prime of beta. This is when beta is greater than 0. This is the classical beta equals 0, balanced. But with beta is greater than 0, the potential is unbalanced. The same for beta less than 0, but it changes. So you have to study this or the E with an unbalanced potential, but for any B. Okay, so what kind of solution you have? Again, you can multiply by ux or u prime, and you arrive at something like this. All the solution of the station solution of the generalized Cahn-Hilliard equation are described by beta and kappa. For any beta and kappa particle, a solution of this is the solution of the Cahn-Hilliard equation, generalized Cahn-Hilliard equation. So let's focus on beta greater than 0. It's the same. The case beta less than 0. This is the unbalanced potential. Every solution, I mean, you can prove that there is a 1-1 relation, no, between the line segment here and the stationary solution. Okay, so for any k between these 2 points, we obtain a solution of this beta, let's say, is b. So what kind of solution? Well, if I choose k equal to this number, the max. K here, periodic solution. They are periodic solutions. So we are not interested in that. They oscillate between this value and this value. When the green line goes here, of course, you oscillate between 2 bigger values. And the time is bigger. But we don't care about this because they are periodic solutions. So the position of the 0 is in some way not arbitrary. They have to repeat in some way because they are periodic. What is very important is when I choose k exactly equal to this. This is an homoclinic solution. Let's say start from here, arrive here, change direction, and go back. Homoclinic. What is the problem of the homoclinic? The homoclinic that exists also for the Cahn-Hilliard equation, of course. The point is, I arrive here for sure in finite time, finite space, and I come back. But what about this? Did I touch this point? It's exactly the same as the heteroclinic solution in the Allen-Cahn equation. In the Allen-Cahn equation, you have your balanced potential. Let's say you move the heteroclinic start from here and arrive here. But you touch or not, or you don't touch. And that the p-Laplacian, the combination between p-Laplacian and potential, theta and p, is important. Here, what is important is to understand if you touch this point. The homoclinic can be not, the homoclinic is something like this. For beta greater than 0 is like this, for beta less than 0 is clear. But the point is, did I touch this point or I don't touch? So you have to do all your computation, etc., and you can prove this result. That, roughly speaking, for any p greater than 2, strictly greater than 2, you touch. So for any p greater than 2, you have new solution. Solutions that are not present in the case of the classical Cahn-Hilliard equation. And this is important. They depend only on p, no matter what is the potential. This result is simply telling you that you touch, that you have an homoclinic like this, but you touch. Since you touch, now it's late, but the point is that when you touch, it's exactly like the Allen-Cahn. You can stay constant as much as you want here. So you can stay constant and maybe then restart. But so you obtain many solutions, but the point is that this distance has to repeat. Now here it's very bad. Forget about this, but this distance has to repeat. So you cannot choose all the n points in a totally arbitrary way. If you have only 2 points, they can be totally arbitrary, also close. Let's say that you have 2 points. You can choose beta because here it's important. For any beta, you have a special solution. So you can choose beta such that your homoclinic is exactly like this. H1, H2. So it's 0 here and it's 0 here. For any H2, H1, no problem. But once you fix B, automatically it fixes the time that you arrive with the derivative 0. Now what happens is that if A and B are here, it's okay. Constant, constant. But if A is here, let's say, you don't, the derivative is not 0, so the boundary conditions are not satisfied. Shortly, for any two transition, for arbitrary two transition, yes, there exists an homoclinic in AT, only if the 2 points are not too much close to the boundary point. So for two transition you have. If you have 4, okay, you can stay constant, but the distance between H1 and H2 has to be the same of H3, H4. So there is no way to obtain other compactons, other stationary solution, when the position is totally arbitrary, the position of the 0. So we can study metastability in the case theta greater than or equal to p. There is no time, only to tell you that there are some differences. For instance, in the case of the Cahn-Hilliard equation, you have to work with the antiderivative of u. The energy estimate is a little bit different because you have the derivative of the energy is equal to not to the integral of u, but u tilde. U tilde is the antiderivative. And I wrote this because it's true for any d, but you have to divide by d. So d equal to 0 is not allowed. D greater than 0, yes. If the solution is smooth, D is smooth, you have a maximum positive, and you arrive at exactly the same relations as before, but instead of the L2 norm of ut, you have the L2 norm of ut theta. This change a little bit the things, you have to work much more technicalities. Actually, the variational result I showed you before has to be true for any, not if u is close to b in L1, but if u tilde is close to b tilde in L1. So there are some technicalities, but you can put exactly the same result for the Allen-Cahn equation. More technicalities, and the result is only on u tilde and b tilde. It's not on u and b. This is not a problem because in the case p greater than or equal to, you can there is a trick to extend this to u and v, paying a little price. Here there is only exponential. Here you have to put exponential of eta, so of eta. So it's, let's say, less, but theta can be any number in 1 minus 2p 1. So if p is equal to, for instance, this is 0, 1. So for any theta in 0, 1, you have this. So you pay a very little price. If p is bigger, okay, you can choose. You have to choose theta bigger, but it's a little price. And again, you have, this is for theta equal to p. If theta is equal to p, you have persistence of for an exponential long time. If theta is greater than p, same result as before with the same constant here. And again, u tilde minus v tilde in general, if p is greater than or equal to, is on u and v. If you want all the details of this result are in these two papers, and thank you very much for your attention. And I'm sorry for finishing too late and arriving very late.
Well, thank you very much for your talk, Raffaele. Is there any questions from the audience or from the Zoom?
Yeah, Rafael, thank you for your talk. I see that this energy technique can be applied in any dimension, no? So I guess the problem will be to find the profiles, no, around you want to perturb, no?
Whenever you consider it in higher dimensions.
See, I don't understand the higher dimension, but what is the question about the
If the problem is to find the profile,
in
Yeah,
dimension?
because
for instance, dimension 2.
all this technique can be extended, no? So
Most of the
so
techniques
the problem may be the effect of the curvature of these step functions, or what's the challenge?
Okay, this is a very good question, Hector. So thank you very much. The multidimensional question is the multidimensional problem is another story, actually another story. But this is true also for the Allen-Cahn, also for the Allen-Cahn, not only for the p-Laplacian. First of all, you lose the phenomena. This phenomena, let's say, for Allen-Cahn. The fact that the solution maintains this profile for an exponential long time is only one dimensional. So when you put the same problem in many dimensions, it's another story. What happens? Well, there is the paper of chain generation of a steady structure. What happens is that, let's consider, let's say, a domain omega. If your initial datum, let's say in some region, I don't know, like the region can be whatever you want, not so bad, of course. Let's say that in some region is positive, even close to zero, but positive, and in other region, negative. Exactly like in the one-dimensional case, for the first, let's say, at the initial time, for small time, it's like you can neglect the diffusion. So where it's positive, it goes to +1, where it's negative, it goes to -1. So you have a transition structure, but instead of having transition point, you have transition surfaces. Okay, so you have to study in 1D, you have to study movement of points. And this is simply, I told you there is an OD, but anyway, they can move in this direction, in this direction, they have a velocity, etc. But they move with exponential small velocity. This is p equal to, it's known as Allen-Cahn. Here, you have to study how these surfaces evolve. And there are a lot of words in the Allen-Cahn case, and they move by mean curvature flow. So there is normal velocity proportional to the mean curvature. But what is the difference is that the velocity in this case is simply epsilon to the power 2. So it is absolutely, remember that the question.
So the question of metastability here would be if the profile is close to whatever, it stays close to the dynamic of the mean curvature flow, no?
Yeah, it remains close, but only for epsilon, let's say epsilon to the -2. The velocity is epsilon squared. And this is simply, if you want, rescale the equation, and then at the time is order 1. It's not slow. If you rescale the model, it's not slow. What about the challenges? Well, the problem is that for the Allen-Cahn case, there are a lot of results, but they use a lot of parabolic technique, like maximum principle, comparison principle, etc. There is a result also by using the energy approach, also by Bronzer and Cahn. Bronzer and Cahn simply say, let us assume that our solution is radial. Omega is, let's say, a ball. Here is +1, here is -1. And they can prove the mean curvature flow, let's say, the evolution of the surface when the surface is active. This is very important because the mean curvature flow, everything, the surface tends to be a sphere and then to move like a sphere. But for the technical point of view, that's my answer to your question, Hector, is that radial is 1D. Okay, radial, you Laplacian in radial coordinates, and you have a one-dimensional equation. So one-dimensional equation when you can apply the energy approach. Of course, it cannot be the same because it's epsilon squared, not exponential, but you can do it. Actually, I would like to study the multidimensional problem, and I will start from this. That is the very basic, the simplest. No, let's start with the simplest. Well, even if you start with the simplest case, I can work on it so much, but the p-Laplacian in radial coordinates is a problem. You write the radial solution. The equation for radial solution is a 1D equation. The hope is to apply the same energy approach. First try, we tried and we couldn't. Now we are not trying anymore. But you want for me, it's a very interesting overall problem. The multidimensional in general, and in particular also the simplest, the radial.
But there is the effect of the curvature playing there, no? So the equation is going to have a coefficient depending on the radius and so on, no? So and degenerates when the radius goes to 0, no? So it's.
Sorry, Hector.
You need to speak up, Hector. Louder.
I'm sorry. So there is the effect of the curvature even with the balls, with the spheres, no? And so you will find coefficients on the ODE that depends on the radius and degenerate when the radius go to 0 and so on, no? So it's delicate.
And this is the simplest. The radial is the simplest.
Okay. Thank you, Hector, for your question. So, Ramon, you have a question?
I have a quick question. With the unbalanced potential, what is the difference when you do the analysis if you apply an affine transformation that makes the unbalanced potential a balanced potential and it doesn't change the energy? What are the technical difficulties or the difference with that?
But you are talking about the stationary solution, no? Or
in the Cahn-Hilliard with the unbalanced potential with the beta, I mean that you have two minima that are not 0, are not the same.
Here, no?
Exactly.
Here.
If you apply an affine transformation linear in U, then you can.
Is that you lose it? You lose it here. When you have the Cahn-Hilliard equation, but this is for Cahn-Hilliard in general. This is f prime of u xz. Now you are saying, if I understood correctly, what if I consider u, my potential, let's say 1 minus u squared plus alpha u plus beta.
Right. And that makes sense. Right.
But the Cahn-Hilliard equation does not change because you have to do 3 derivatives.
Right.
F prime here, xx.
Right.
So when you do the first,
Right.
when you do the second, so actually it's always the derivative of this.
Yes.
So the point is, for any potential of this form, you have solution of the Cahn-Hilliard equation. And the difficulties here, the question is about the difficulties in here, but to prove this, to prove the
Right. Because the energy doesn't change. I mean, the energy is going to be the same because it involves only
but,
derivative.
I mean, why you touch? Because for p greater equal 2, you don't touch for it.
Okay.
The point is that you have to study this for the case fixed is exactly g beta in u minus. So you have to study this ordinary differentiation. And when you do a separation of variables, the same problem as before. How much space I need? P greater than 2, you find out that only for p greater than 2, you touch.
Yeah, actually, the ODE changes.
The ODE
I
changes.
mean, the energy doesn't, but the ODE for
The ODE changes. And it's very nice for me, for us. It's very nice that these pools that touch exist for any p greater than 2, no matter what is theta, no matter what is the potential.
Thank you. And any other question? Well, if not, it's a little bit late, so let's thank Raffaele again. Let me stop recording.